Yeah, hi everyone. So my name's Robbi. I'm going to talk to you about our work mapping Australia's coastline in 3D through time using the Digital Earth Australia archive of satellite imagery. So I'm from the Digital Earth Australia program at Geoscience Australia. And so we manage, our sort of role is to manage Australia's official archive of satellite imagery. And so this is about, I think it's about 37 or 38 years of data now. About 2 petabytes in the cloud and about another 8 petabytes on the national supercomputer. So huge amount of data. And this is really sort of the amount of data volume that we're dealing with was one of, sort of the impetuses for creating the Open Data Cube. That if you were here yesterday and you saw Paul's talk, it was sort of designed to help us sort of manage this sort of really large volume of data. And so the nice thing about the Digital Earth Australia archive is that a lot of the processing work that you normally have to do the imagery is already done to the imagery when we index it into the data cube. So sort of all of that really hard stuff like calibration and pre-processing is all done, and so the data is in this sort of analysis-ready format. So theoretically, you can sort of start jumping into the actual fun science stuff much quicker and easier than having to do all that stuff yourself. So the sort of specific environment I'm going to talk to you about today is called the Intertidal zone. So this really, if you've been at the beach and you've watched the tide go in and out, this is really the area between low tide and high tide. So the entire area that the ocean covers at any point. And so this is it's a very important area, like it's of the place that people interact with the coastline, interact with the ocean. But it is actually a kind of a funny area because it's not really land and it's not really ocean. It's periodically wet, periodically dry. And so what we sort of find is that this area kind of slips between the cracks of our national mapping efforts. So on the bottom here, we've got on the left our Elvis platform of terrestrial elevation data. On the right, our Oz seabed platform of marine sort of bathymetry data. And what we find is that because this environment's really difficult to survey, because it sort of has these changing conditions and it's wet and muddy and sometimes quite treacherous, it kind of slips between the cracks and we end up with this sort of consistent data gap along our coastline. And so for us as Geoscience Australia, as a sort of national mapping body, having this sort of gap in our national data holdings that describe the shape of our coastline is a bit of a problem. So a few years ago, in 2019, we sort of published the first data set to try and solve this issue. So this was a Landsat-based data set, and we sort of used the rise and the fall of the tides to map the extents of this intertidal zone. And so at the time, it was the sort of first 3D model of the coastline, but it did have some major problems. So it was, because we were using Landsat, it was quite low resolution, 25 meters at that point. It was also one single model. So the method we used needed a lot of data to run. So we kind of generated just one elevation model for the coastline that sort of was meant to represent 30 years of data. And because the coastline is so dynamic and so constantly changing, this is a pretty massive assumption. And really, in reality, for lots of places in the coastline, this wasn't a very good fit because the coastline just changes so frequently. And we also used some sort of interpolation methods to get more detail from the data, and it meant that some of these really fine-scale features on the coastline that are actually really important, so sort of habitats for different species, were kind of averaged and blurred out. So it was a good sort of first attempt, but there was many places that we could do better, and this is sort of the reason for this bit of work I'm going to show you now, is trying to sort of improve each of these 3 things: the resolution, the time aspect, and the sort of the smoothing out of the data. So the model that we came up with to try and improve our mapping is actually quite simple, which was a nice thing. It's always good when you can get a sort of a quite simple mental model that then helps inform the satellite remote sensing. So here's a sort of an example of a typical beach. We're interested in this dot here, this sort of star, and so you can sort of imagine that that's a dry pixel. What we find is that when the tide is low, that pixel is dry. As the tide increases, it stays dry to a certain point. As the tide rises over a certain point, that pixel goes from dry to wet. And then at every tide height from that, it stays wet. So this is a relationship we see all across the coastline, and it's a quite sort of characteristic, easy to identify threshold where sort of this pixel goes from being dry at low tide to wet at high tide. So another way of looking at it is top down with satellite remote sensing imagery. So same thing on the right, the star is our pixel we're interested in. You can see as the tide goes in and out, this is Landsat imagery sorted by tide. That pixel will be dry at a certain point and it will shift to wet. And you can see here on the sort of tide height axis on the x-axis, we sort of see this jump where it goes from dry, 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 and then suddenly wet, and then stays wet after that point. And the nice thing about this relationship is that terrain wetness is something we can map really easily with satellite data. So we can use something like a water index, NDWI, and we can sort of track the exact point where that pixel jumps from dry to wet. And then if we identify the tide height where that happens, we can use that as a proxy for elevation. So to do this at sort of scale, we access a space-time chunk of data from the data cube. So we load all available satellite imagery for a certain year. And then using that satellite stack, we then use tide modeling to identify the tide height for every pixel. And so we're not really doing this on imagery level, we're doing this for every single pixel through time. And at the final slide, I'll show you some new open source tools that we've just published recently that sort of makes that step a lot easier. So the idea is basically you get a stack of satellite data and a stack of tide heights, and then you can interrogate each pixel and develop these relationships. And so this is based on, the tide modeling we use is based on a really awesome open source package called PyTingMD. And we've also developed some satellite remote sensing tools that build on top of that in the EO Tides package. So essentially we're doing what I showed in the previous slides. We're building that relationship up for every pixel. So you can see here on the left graph, this pixel shifts to wet really quickly. So the really low tides, so its elevation of that pixel is quite low. And then the one on the right, it takes a lot longer for it to go wet, so its elevation is much higher. And we can sort of scale it up across the whole country, the whole continent, and get an estimate of elevation for every coastal pixel. So this is what our original data set looked like. This was the NIDIM data set we published in 2019. So it still captures the general shape of the coastline. You can see the yellow pixels are high elevation near the coastline, blue pixels are deeper. But it's quite blurred and smooth, and you can see some of the 25-meter pixel boundaries in there. So kind of doing an okay job at capturing the rough shape, but not the detail. And this is what we get when we apply our new method. Suddenly all of this new detail pops out. We're sort of seeing these really micro tidal channels in these tidal flats. These are sort of often excellent habitat for different fish species, different intertidal macroinvertebrates, different sort of seagrass. So these features are what we really want to be capturing for habitat mapping and sort of really understanding the processes that influence these coastal environments. A really big part of what we do with our coastal products at GA is trying to make sure our validation is at the scale sufficient enough to sort of get a decent idea of whether we're doing this mapping accurately. And so we're sort of lucky enough to have these amazing data portals like the Elvis portal that contains aerial LiDAR data captured over the last 10, 20 years. And so we've been sort of scaling up our validation across as many coastal environments as we can to try and work out where these models work and where they don't work. So you can see on the right here, here's a sort of a typical aerial LiDAR over a tidal flat in the Gulf of Carpentaria. You can sort of see the nice detail in that one. If we pop on the model data, we can see that we're picking up really similar patterns. And often in some places, because we're able to get satellite imagery across the whole tide range, we can sort of capture some of these low tide tidal flats up the top that aren't captured in the LiDAR data, mainly because the LiDAR can only fly over. They sort of try to target low tides as well as they can, but it's really difficult when you're flying a plane and conditions change on the ground to sort of get that timing right. So there are some places where we can actually capture some extra areas that would be really expensive to capture with LiDAR. So validation results, what we find is that the accuracy of the model is actually pretty consistent across different tidal environments. So we generally can pick up elevation to about 30 centimeters. Obviously that means that if your tide range is only a meter, 30 centimeters accuracy is pretty terrible. So that's the left example. And so this means that this model isn't great for most of East Coast Australia, a lot of South Coast Australia. It's really targeted for these big tidal flats up north where the tide can sort of go up and down by 10 meters or so and out by hundreds of meters or kilometers. So it's not a product that's designed for mapping coastal change across a lot of, our more steep wave-dominated beaches, but it does work really well up north where we have these very big tidal flats. One sort of thing with these products is that it can be really valuable to know how well you can rely on it in certain environments. So we know these models work well in some places and not well in others. So with this data, we've packaged this of a modeled uncertainty layer that gives you an idea of just how well we think we're modeling the elevation. And the nice thing is that this, even though this is a modeled uncertainty layer, it does correlate quite well with accuracy in the validation sites we have. So you can kind of use this to work out whether the model's reliable in a certain location or whether you probably shouldn't be using this data set at all. And what we find is that often it works well in kind of quite static environments. It doesn't work very well where there's sort of really rapidly changing creeks that are changing more frequently than the annual epoch we're studying. So yeah, if you've got sort of these sort of really dynamic environments, this won't work. If you've got something that stays relatively consistent across a year period, it often works quite well. So the really cool thing though with this is that because we're using a huge amount of Sentinel-2 and Landsat data, we're not restricted to doing this on 1 year period. So this is really sort of where we wanted to get to. with this study. We wanted to sort of track change through time. And so these are about 6 or 7 years of digital elevation models animated through time. And you can sort of see some of these movements in 3 dimensions of these big sandbanks moving over time, sort of migrating slowly. So I think the one on the right's at the Burdekin River. This is a huge sandbank. I think it's about 5 kilometres long that's been slowly moving inland. And so that suddenly we're sort of going from a static view of our coastlines to a really dynamic 3-dimensional view, so sort of mapping things in 4 dimensions over time. That then means if you have multiple elevation models through time, it means you can start to do cool things like differencing them. So here we've got red are pixels that have decreased in elevation over time, blue are pixels that have increased in height. And that then means you can start to sort of sum up these changes, kind of calculate volumes of sediment that are changing. And that's potentially going to be really valuable information for monitoring how sea level rise is affecting coastlines and sort of how much sediment is moving, where it's moving to, and what areas are likely to be more vulnerable with sea level rise. And yes, so this is something that we can sort of, this is visualized in the Terrier platform. We can do this sort of on the fly in Terrier, and then scale this up across the whole country and sort of look at these stats on a really big national scale level. So all of those results were quantifying vertical change, so sort of tracking how these features are changing through time. But you can see here on the right, this Burdekin example, really very little of the change that's happening here is vertical. So there is some changes, some pixels are decreasing, some pixels are gaining elevation. But really, most of the change you can see here is sort of movement of sediment. So these sandbanks moving horizontally, sort of shifting through the landscape, not necessarily losing sediment, but just sort of changing their location and sort of shifting over time. And so these are sort of the geomorphic processes that are really fascinating. And so our sort of next step is working out how we kind of go from looking at just change to change in sort of spatial dimensions as well. There's some really neat sort of approaches for doing this that already exist. So this is optical flow vectors are essentially a way of tracking movement between video frames. So these are usually used for sort of video applications. I think Tesla cars use this for sort of tracking features that they encounter as they drive. But they can be applied to any time series imagery. So we can apply this directly to our time series elevation data and start to look at change sort of in this sort of horizontal, sort of spatial directions. And so what you get out is basically a set of vectors, of arrows, where long arrows are fast movement, short arrows are slow movement. So this is an example in Bird Island. This is a bird sanctuary just north of Adelaide. You can sort of see here on the right, just visually with your eyes, you can see that the sandbank's moving sort of to the northeast. But if we run an optical flow vector analysis on it, we get these arrows out, which sort of seem to line up pretty well with the sort of patterns we're seeing visually. And again, this is something that is pretty fast. I think this is all based in scikit image. There's some really fantastic libraries in there for doing this kind of thing at scale. And this is something that we can scale up to really big scale and sort of start looking at movement of sediment at sort of regional or continental scale. Again, this is a more complex example. There's sort of like an eddy of mud that's moving on land in the Pilbara here. Again, we can kind of pick up these patterns with these vectors and sort of start to track this sediment in really sort of quite detailed. So in the past, one of the things we've struggled with in DEA is that because we're developing these products for Australia, all of our workflows are kind of optimized to work in Australia, and code ends up being quite bespoke. It ends up being quite challenging to apply them outside of Australia. And I think the Digital Earth Pacific crew have had some of those issues with some of our coastlines data. It was very much an algorithm that was designed for Australia, and adapting it to work in the Pacific was a bit tricky. So one thing we've really tried to do in this product is make this a bit easier by separating our data loading code, which is often where the most bespoke stuff happens, from our analysis code. And so we've really been relying heavily on ODC Stack or on Stack metadata for this, because it sort of lets us kind of treat the loading code as a module that you can plug in any sort of source of remote sensing data and then run the analysis code on that as long as it's got consistent formatting. And so Stack is a really powerful tool because it lets us access data anywhere in the world in a consistent way, time series data just like we get from Australia, but for anywhere on the planet. And so, yeah, this is, I think, again, some of Alex's code. 6 lines of code lets you load satellite data for anywhere on the planet, any time period, anywhere. So this is some just fun examples we've run using our algorithms in Incheon. So if anyone's flown into Seoul, you'll have seen these huge tidal flats that go out 10, 20 kilometers into the ocean at low tide. And in Grays Harbor in WA, some really nice tidal flats in a sheltered estuary. So all of these algorithms can be applied pretty easily now with Stack to anywhere on the planet. And we had a sort of a quite fun interaction with some people from the San Francisco Regional Water Board who had a meeting with us asking us about how they could use their products. And we kind of got to the meeting and they told us they'd already downloaded the products and were already running it and had already generated some data. So it was a pretty cool example of just how easy Stack makes some of this stuff. So just to finish up, the Digital Earth Intertidal product is all available free and open data online. So there's metadata there describing sort of where it works, where it doesn't, and then how to access the data. And so this sort of comes with elevation, uncertainty, and then some other layers that help you contextualize it. The other thing that's brand new is this EO tides package. So a lot of our work fundamentally relies on the accuracy of our tide modeling. So that's sort of getting water level heights for every pixel. And so we've recently wrapped this up into a Python package, an open source Python package that does all of this sort of analysis I've shown here today. That's sort of estimating tide heights for every image through time. And so you can get this on PyPy and sort of start to explore some of these sort of tide-related processes. Just to finish up, I'll just put on a slide of basically the patterns of tides over the last week of this conference. And happy to take any questions.
Thank you, Robbi. We have time for a few questions. I see one here.
Thank you. A quick question. CSRO produces climate change models and gives us sea level rises. How hard will be kind of projecting those based on the tiles and so on?
Yeah, so I guess a big limitation of our current approach is that we just use tide heights. And there's a whole lot of other sea level influences that could be included. Basically, the more accurately you can model sea levels, the more accurate these models will turn out to be. So yeah, if there's a model that we can plug in that gives us a sea level height for any sort of location and time, that should be able to pretty easily plugged in. And it would be really, very cool next step, I think.
Robbi, you mentioned that these models are really only good for areas where there's like long or large, I guess, tidal areas. On the East Coast, we tend to actually fly a lot of LiDAR. Can that be utilised in a way that then we can see some of these results on some of those other areas?
Yeah, so some of the, so for their optical flow stuff, particularly, I think if you have two LiDAR acquisitions, you can start to look at them in the same way and get sort of track sediment through time. I guess none of our models are pretty data intensive, so you need a bunch of satellite images to get good results out of them. So you wouldn't be able to just plug in a couple of LiDAR and use it. So I think we kind of see it as being complementary. So I think in the East Coast states, often they do fly LiDAR, and that's probably a far better model than what we're going to produce. But for sort of up north, it's just simply way too expensive to fly any sort of intensive survey at the scale you need to get these places mapped. So yeah, so I think the idea is that they're probably complementary. The East Coast states will keep using the really, really detailed LiDAR stuff, and then the rest of the country, this might sort of fill in some gaps.
Any other questions? Okay, so thank you, Robbi, for your great presentation.